Okay, so in this video today, I just wanted to run through the calculations that accompany chapter 18, which is pH and indicators. So I have used the revision book examples here. So this first example, 18.1, is on page 152 if you want to look it up. But so I'm just going to go through it here now. Okay, so they have asked you here to calculate the pH of a 0.1 molar HCl. Okay, now the first thing here is that you must remember is that these are both strong acids. Now in chapter 12, you have revised the definition of an acid. What is an acid according to Bronsted and Lowry? An acid is a proton donor. Now these are strong acids. What does it mean to be a strong acid? It means that they are good proton donors according to Bronsted and Lowry. Good proton donors. So remember we spoke about like 99.9% association, wasn't it? And look at the arrow. The arrow means that it goes to completion, which means that 99.9% of these HCl molecules will dissociate to produce H plus and Cl minus, okay? So these are both strong acids. Nitric HNO3 would be another example of a strong acid that you would have learnt about in chapter 12, okay? So look for the arrow going to completion. Strong acids will completely dissociate, 99.9% dissociation. So the equilibrium lies very much over here to the right-hand side. Nearly all of the molecules dissociate to give you H plus and Cl minus. So in chapter 12 as well, they would have asked you about the strength of conjugate bases. Do you remember? So like this is a strong acid here, HCl, okay? So the HCl dissociates completely and gives you H plus and Cl minus. This is the conjugate base. What would you say about this Cl minus? Does this have much of a tendency to act as a base, accept a proton, and go back over to the HCl? No, it doesn't. Why not? Stronger the acid, the weaker the conjugate base. It's going against the equilibrium completely by trying to drive it over here again to the left-hand side. So you would say something like that. Strong acids produce weak conjugate bases. Very little tendency for this to go over to the left. So the equilibrium lies very much to the right-hand side, okay? So the stronger the acids, the weaker the conjugate bases. Okay, now, just going back to the calculation that we were asked about here. So you were given the concentration of the HCl, right? They told you that it was a 0.01 molar HCl solution. So you have the concentration. It's a monobasic acid, HCl. So your ratio there is 1 mole of HCl, 1 mole of H plus. So if you have 0.1 moles of HCl, you will produce 0.1 moles of H plus, and then fill that into your pH formula as your hydrogen ion concentration. H plus ions, remember, are hydrogen ions. So that goes in there and you get out your pH of 1, okay? Be careful with something like sulfuric acid. Sulfuric acid is a dibasic acid, so the ratio is 1:2. Okay, so it's a 1:2 ratio here. So if it's a 0.1 molar solution of sulfuric acid, H2SO4, you're actually going to produce 0.2 moles of H plus ions. And that's what you fill into your pH formula then, and you're going to get 0.7 when you put that into your calculator. Okay, so remember your formula again to calculate pH, minus the log of the hydrogen ion concentration. You must have square brackets because square bracket indicates concentration in moles per litre. Okay, strong acids there, all right, and complete dissociation, that's what you need to think about. All right, in the next example here now, lads, you're given the pH, okay? Now, if you are given the pH of the solution, then you need to work backwards, if you like. So you were told here, look, so your pH formula minus the log to the hydrogen ion concentration is your pH formula. That is equal to 1.5. So what would we have done then? We'd have brought over the minus. So the log, so if you have written down that the pH equals minus the log to hydrogen ion concentration equals 1.5. You bring over the minus, remember? So then you have log of the hydrogen ion concentration is equal to minus 1.5. And then anti-log minus 1.5 gives you the hydrogen ion concentration, okay? So remember that if you're given the pH at all in the question, which you are here, if you're given the pH in the question, then you can calculate the hydrogen ions. So watch that in the exam questions. So if you're given pH at all, you'll be able to calculate the hydrogen ions, okay? Now, you have the hydrogen ion concentration here now. But the other twist to this question here is that it's a dibasic acid. So look, 1 mole of H2SO4 will dissociate to give you 2 H pluses and SO4 minus 2. So look, the ratio is 1:2. So in this instance here, okay, your hydrogen ion, so your ratio is 1:2, okay? And your hydrogen ion concentration here, your hydrogen ion concentration here is 0.0316. So what would be the concentration of the acid? You have to half it. Okay, see them halving it there? Because the hydrogen ion concentration is twice the concentration of the acid. Okay, now in the next question, and very often actually it happens like this in the exam questions where they don't actually give you the concentration of the acid or the base. They give you, grams in a certain volume. So remember, now he does it out a little bit funny in the revision book there. What would we have done? We would have said, well, if you've got 2 grams in 500 cubic centimetres, what would you have in a litre? You'd have 4 grams in a litre, because a litre is 1,000 cubic centimetres, so I'll be multiplying by 2 there. And then you want to change grams now to moles. Now, it's sodium hydroxide. When you work out the MR of sodium hydroxide, it's 40 grams. So you're dividing 4 by 40. So you're getting the 0.1 molar here that they're getting. So we did it out a little bit differently when we were doing those. So 2 grams in 500, 4 grams in a litre. And now you want to convert mass to moles. Watch, you have a formula for that, haven't you? Mass all over relative molecular mass. And you're getting your 0.1 molar. Now you have it in molarity. Then you're reverting back to the way you would have done the previous examples. If it's a 0.1 molar solution of sodium hydroxide, you're going to make, look, 1:1 is your ratio. So you're going to make 0.1 moles of OH minus ions, because it's a base this time, remember. Okay, so bases dissociate to produce OH minus, don't they? So it's OH minus ion you're filling in. You're being able to calculate the pOH of 1 when you fill in that concentration into OH minus ions. And remember that to get the pH, then you have to subtract from 14. You subtract the pOH from 14 to calculate the pH, okay? Remember now, lads, that if you asked for the pH of a base, your answer will have to be greater than 7, okay? So 1 would not make sense. A pH of 1 would not make sense to me for the pH of a base. It has to be more than 7. So then you'll say to yourself, oh yeah, I have to subtract from 14 to get the pH of the base, okay? Now, in the next example here now, look, we're given a Ka value. The minute you see a Ka value, you are thinking, this is a weak acid, so you need to use your other way of calculating this, right? Remember we had a formula here, look. So hydrogen ion concentration to be squared is equal to the Ka, which is your acid dissociation constant, and Ma is the molarity of the acid, okay? Now they asked you here in part A to write out the acid dissociation constant. So you're just putting the products over the reactant, and watch, has to be square brackets, okay? Part B then, you're asked to calculate. Now you have the molarity, so you have the Ma, it's 0.2. And you have the Ka, 1.7 by 10 to the minus 5. So when you fill that in and square root both sides now to get rid of the hydrogen ions concentration to be squared, and you get your hydrogen ion concentration. That's your hydrogen ion concentration. Then plug that in to your pH formula to calculate the pH of the weak acid. Okay? So remember, the minute you see a HA value, you are straight away thinking, oh yeah, this must be a weak acid. Okay? Now, here they're asking you to calculate the pH of a 0.2 molar solution of nitrous. Lads, be careful that you don't mix up nitrous with nitric. Nitric acid, HNO3, is a strong acid. Nitrous acid is a weak acid. How do I know here? Because it's giving me a Ka value. Or, sorry, it's not. It's asking me to find its Ka value. So I know it's weak. Okay? Now, the very fact that I'm being told the pH, try to get into your heads. If I'm given the pH, first step, straight away, is I use my pH formula to calculate the hydrogen ion concentration. So it's anti-log of minus of the pH to get the hydrogen ion concentration. Now that I have the hydrogen ion concentration, I can fill it into this formula here that we would have had. We would have always have written hydrogen ion concentration to be squared equals Ka times Ma. So you write that and then you fill in your hydrogen ion concentration. You know the molarity is 0.12, but you don't know the Ka. Okay? And then you manipulate, divide both sides by 0.12 there to get the Ka value on its own. Is that okay? Now, Finally then, they've asked me about the KB. So it says to write out the KB expression. So they've written it out there, look. So the KB expression, again, look, products over reactants, but be careful that you have the square brackets. You must have the square brackets. So that's that. Now, calculate the pH of, again, look, it's giving you the concentration of the weak base and it's giving you the KB. Look, similar equation for weak base, but it's OH minus ion concentration to be squared if it's a base, KB and MB. You're told the MB is 0.2, but it's not giving you the sorry, now, what's not giving you here? Oh yeah, sorry, it is giving you the KB. So you are just going to calculate the OH minus ion concentration by getting the square root of both sides. So you're filling in here, you have the MB, you have the KB. This is my OH minus ion concentration. Fill that into POH and you're getting 2.72. Now a POH value of 2.72, remember you must subtract that from 14 then to calculate the pH. And remember we said that pH of bases would have to be greater than 7. So make sure that it's greater than 7. Okay? So remember there now again. So if I just 2 seconds now, I just want to go back a second here to the weak, where we had the weak acid, okay? Weak acid. Here, as you see the way here, you would have had a weak acid. What would we have said about weak acids? Little tendency to donate, okay? So we would have said that the dissociation constant, just use a different color for a second, I'll use the green. Dissociation constant here, 1.3%. Look at your reversible reaction arrow, does not go to completion, only 1.3% dissociation. What does that mean for the weak acid? 1, say, out of 100 of the ethanoic acid molecules will dissociate. So the equilibrium lies very much over here to the left. This is the conjugate base. What would we say about the strength of the conjugate base? It's quite strong. Good tendency for this to accept the proton and drive it back over to the left-hand side. So weak acids, okay, have strong conjugate bases. Strong acids like the HCl, weak conjugate bases. Okay, thank you.